Hello, my name is Dave Kress. I'm the Director of Technical Marketing at Analog Devices, and I'm going to be doing the first half of this session on sensors for low-level signal acquisition. And Nitzan Gadish, an applications engineer in our MEMS group, will be discussing motion and microphone sensors. First have to say that our lawyers have asked us to tell you that this material is all copyright. We will allow you to use it in your publications if you ask, and if you will cite us in your publication. You're also, of course, welcome to use any of this information in your design work, and we encourage that. What we're going to cover today are that sensors are the source of information about our environment. They can be difficult to use, and we need special signal conditioning for them. We're going to look at silicon sensors, especially designed for this, high accuracy applications, and then focus more on motion and microphone sensors later in the presentation. Our real world is not digital, and in fact it's not even electronic. Everything that we're interested in, such as heat, airflow, sound, all of those things are physical variables that are not usable in their form unless we figure out a way to sense them. So what we do is to employ sensors, which will provide an electrical output in response to a change in the physical variable. We then take the output of those sensors through amplifiers, which improve the signal. Then usually we'll put them into data converters, and it will feed back around to our actuators to either transmit or make some change to the physical world. There are many types of sensors, and we are so interested in gaining information about the physical environment that we employ many different types of changes in the electrical properties of a sensor. A standard one, of course, will give us a simple voltage, such as a thermocouple, but also we will measure the change of resistance of a device as the physical variable changes, capacitance, charge, any other factor. One interesting thing about sensors is that they are also actuators, in that if you were to reverse the function of the device, say with a microphone, and put a voltage across it, it would actually make a sound. And of course, those are speakers. Any one of these can be reversed, and of course actuators can be reversed in function. But in order to get a usable signal, we need to improve that signal, typically with an amplifier that will then lower the source impedance, get rid of some of the noise, maybe linearize it, but then improve that signal so that it's much more usable for us in our electronic analysis. In order to make that a lot easier, we have taken to designing as many sensor types as we can in silicon. A couple reasons for that. One is that connecting silicon to electronic systems means you have long wires in many cases, which will pick up noise and cause other problems. But if we design the sensor on the same chip as the amplifier or even A to D converter, those lines are a lot shorter, and we can customize the electronics so that these things work very well together, and we're going to look at that. The silicon sensors that we've done, of course, are of a similar range of capabilities as the general sensors that we showed on an earlier slide, and again, we're trying to take advantage of any change that we can find in the sensor, the current output, the resistance, change in capacitance, in order to extract an electronic signal. And we've been able to measure just about anything in silicon that can be generally measured. So we've made a lot of progress. If we look at sensors on a historical basis, they originally were used for measuring weight. Some 7,000 years ago, and that's because it was used for commerce. How much grain for how much money. Temperature, which is still the most widely measured function or physical variable, came in for the next round of sensors, and of course our friend Galileo started that out with the thermoscope, which is something as a toy you can buy today. But we can see here that if you want to get your name on something, what you want to do is to put a scale on it, as Fahrenheit and Celsius, and of course Lord Kelvin invented absolute zero. But the first usable sensor that gave us control was a thermostat, which was invented by William Johnson in 1883. Today there are many types of temperature sensors. This is just a few. The thermocouple may be the most widely used, especially in instrumentation and industrial applications, because it can give us such a very wide temperature range. RTDs and thermistors give us very high sensitivity, but lately semiconductor sensors for temperature have become very popular, again because they are built right on the silicon and they're quite a bit easier to use. A silicon temperature sensor is actually quite a simple device and simply uses the delta VBE, base emitter voltage, which results from the same current flowing through two transistors of different areas. And we can see that that delta VBE is proportional to absolute temperature T over a very wide range. We've gotten these to work down to liquid nitrogen and to well over 200 C. They can be built up into a more complex circuit, such as this Brokaw cell invented by Paul Brokaw quite some time ago, and this would provide a voltage output. It also is a way to build a low temperature coefficient reference, and it also can be configured so that it's a current output device. This turns into a variety of analog output temperature sensors, which began with the AD590 over 30 years ago, and they provide a range of outputs, either a current output, which is quite easy to use with a 2-lead format, or a voltage output for other configurations. Now, since it's done in silicon, we can then add an analog to digital converter onto the same chip to give a digital output temperature sensor. The key, of course, is to make the A to D converter very low power so it does not heat up the sensor, and then you're measuring the temperature of the A to D instead of the environment. We've been able to get this to very high accuracy now with our ADT 7420, 7320 series that can get down to 0.2 of a degree C. And this is useful for many applications, as well as the ability to interchange the sensors without calibration. Newer applications and even older applications are demanding more and more accuracy from our temperature sensors. And this is a variety of what those are. In order to get good process control, you need good temperature control. And the demands keep getting higher and higher in that area. Now, if you want to go to high performance and high accuracy, there's many ways to do it. The digital IC, our ADT 7320 series, is quite easy to use and has very few limitations. If you want to use a device such as an RTD or thermistor, possibly because you have a mounting problem or you need a wider temperature range, they can also be used, but you need to account for their limitations. We'll look at the thermocouple here briefly. because it's the most widely used temperature sensor, especially in industrial applications. It's also an interesting electronic problem to solve. The biggest reason for using the thermocouples is their extremely wide temperature range. They can get out over 2,000 degrees C and go down as low as 184 C or below liquid nitrogen. So they have a very wide range. They have a low output for most of them, and we need to compensate for that. The most popular are the J and K, mostly because they have among the highest output ranges. The output, which is known as the Seebeck coefficient or the microvolts per degree C, is fairly low. It's also nonlinear, and we need to have ways to compensate for that. The way that they work is that they're essentially a small battery, which produces a thermoelectric EMF, which is what a battery does, and that changes with temperature. At T1, if you increase the temperature, that EMF will go up. The problem is that since it's two different kinds of wires, when you connect it to your measuring instrument, you're also connecting to two even more different kinds of wires. That creates another thermocouple, and if you don't compensate for that effect, you will get errors. This is known as the Cold-Junction, and there are many ways to do it. One is to freeze it at a constant temperature, or another way, which is much more common now, is to sense that temperature at the cold junction and compensate for it. We've done that with a series of thermocouple amplifiers, our AD849X, which includes a high accuracy instrumentation amplifier as well as the cold junction compensation. Runs at very low power so that the self-heating does not induce errors. It's a fairly low cost device and works over a fairly wide temperature range, and these are quite popular. You can build up a whole system, and our circuit note or circuit from the lab, CN0271, shows a complete circuit for capturing the signal from a thermocouple through a buffer amplifier and into a high-resolution A to D converter. You can also do cold junction compensation with our newest digital temperature devices, the ADT7320, and you place the ADT7320 as near as possible to the cold junction or reference junction, and then take that temperature and put it into the digital system along with the measured signal. This helps because it can compensate for nonlinearity and may make it easier to do the measurement entirely. This would show an application for doing that. The white connectors on the right side of the board accept the input from the thermocouple, and the ADT7320 is right next to it so that they're both at the same temperature. If you want to use the RTD, resistance temperature device, where you need to measure change in resistor over temperature, our AD7793 provides excitation and instrumentation buffer amplifier as well as a high resolution A to D converter to get high accuracy measurements from these devices. Now let's look at high impedance sensors, which are used for a variety of things, such as chemical monitors and other operations. But we're going to focus on photodiodes because they are certainly the most widely used type of high impedance sensor. Most of them, of course, will interface to an FET type amplifier because of their high impedance nature. A photodiode is actually a very simple device. It's a bit of an analog to a thermocouple in that a thermocouple puts out a voltage in response to temperature, whereas a photodiode puts out current in response to light and requires no external input in order to provide that current. Can be used in a couple of ways. For precision application, we use the current directly without a bias and run it through an amplifier. For higher speed applications, particularly in communications, we will put a small voltage across it, and that tends to speed it up. Photodiodes can run over an extremely wide dynamic range, and we see here 6 orders of magnitude from 30 picoamps to 30 microamps, from almost dark to direct sunlight. And they're very accurate over that full dynamic range. But if we want to use that type of dynamic range, we need very good signal conditioning around them. The circuit is actually quite simple, but we need to pick the amplifier very carefully for the type of sensor and application that we have in mind. In order to do that, we've provided our analog photodiode wizard, which is easily found on our website. It allows you to put in the parameters of the sensor and then some aspects of your applications. You then calculate what the response will be. The wizard then gives back suggestions of a few amplifiers that would be ideal for this application. You can pick one of those, and then we will give back a circuit employing that amplifier as well as the additional components needed to complete the circuitry. This is also available with a SPICE macro model to put into your own designs. This also can be built up into a more complete circuit, such as our circuit note 0272, which is used for a variety of applications, including colorimeters. There are also sensors, a wide range of sensors which are built, resistors which are built up into bridge circuits, which is 4 resistors in a diamond configuration, used for many applications. Strain gauges, thermistors are built up this way, and of course it measures the change of resistance with the change in a physical variable. We have another session which is our Instrumentation and Sensing 2 session, which goes into those sensors in much more detail. We also are going to look at motion and position sensors. We have a variety of those, interface for LVDT, Hall effect sensors, and others for magnetic sensing. We have a variety of rotational position sensors, but for the rest of the presentation today, we're going to look at a sensor which measures acceleration. Also, by employing that, can measure rotational motion as well as sound in microphones. And this portion of the presentation is going to be covered by Nitzan Gadish, who is our MEMS application engineer.
Thanks, Dave, for the introduction. MEMS sensors today are everywhere. They're in applications and devices ranging from cell phones to automotive applications, both for safety and for infotainment, to medical devices, health and fitness products, to asset tracking, military applications like avionics and navigation, industrial applications like fleet management and precision agriculture. Just about every industry today has some use for a MEMS device. The reason MEMS devices have become so popular is because they help our systems understand our motion, and in that way they make our interactions with electronic devices more intuitive. So let's look at some of the types of motion a MEMS sensor can sense. First kind is, and perhaps the most obvious, is linear motion. Sensing linear motion is useful in applications that move forward, backward, along a straight line. So things like trucks or vehicles, robot arms, etc. Another kind of motion we can measure is tilt, and this is actually a very common thing to measure. Tilt measurements are very useful for, well, measuring and reporting tilt, or for using a tilt measurement to stabilize a platform. Some applications that measure where tilt measurement is needed are things like hospital beds, electronic levels, antenna towers, things like that. Another type of motion you can sense with a MEMS sensor is shock and vibration. These are just like linear motion, only faster, and in the case of vibration, repetitive. So a vibration could be thought of as back and forth linear motion. Some applications where shock detection is very useful are things like acid abuse, so did you drop what I gave you, and concussion detection, which is becoming very visible in today's sports world. Vibration detection can help predict, for example, when bearings in a machine or in something that's rotating are not running smoothly. For example, when a washing machine isn't balanced, or say when a windmill is vibrating due to excessive wind, for example. Another sense of motion that we can measure is rotation. This can also be sensed using MEMS sensors. And rotation is useful in applications like rollover detection and optical image stabilization. Last but not least, you can combine multiple types of motion measurement into what's called an inertial measurement unit, or IMU, which refers to a combination of multiple sensors. IMUs are, the IMUs made by analog devices are generally used in very high precision applications. These are some applications that require this level of precision. So high precision or high-end agricultural equipment and military and aerospace applications such as UAVs, helicopters, etc. So these are the 6 types of motion that are measured by MEMS sensors, and all 6 of these types of motion can actually be measured by 2 sensors. These are accelerometers and gyroscopes. Accelerometers measure linear motion, which also happens to include tilt, shock, and vibration. Gyroscopes are the ones that measure the rotation, and an accelerometer and a gyroscope put together can be combined to make up an IMU. So let's start by talking a little bit about accelerometers. Today, Analog Devices is one of the largest manufacturers of MEMS sensors, but how do we even get into the field of MEMS? Well, we started out in about 1986 with a product concept for an airbag crash sensor, so a sensor that would sense a crash in a car and send a signal to deploy the airbag. Before accelerometers, the original crash sensors for airbags were mechanical. One common design was this ball and tube design. So a magnet at one end of the tube holds the ball in place during normal motion. So this is normal motion. And then in a crash, the car undergoes a large deceleration. During that deceleration, there's enough inertia to cause the ball to dislodge from the magnet and move to the other end of the tube. When the ball makes contact with the other end of the tube, that pushes in a switch, and that triggers the airbag to deploy. So this is a mechanical way to take advantage, I guess, of the principle of inertia to sense a crash. That principle of inertia is also exactly what makes our accelerometers work, and that's why they're sometimes referred to as inertial sensors. So in the case of a MEMS accelerometer, instead of a ball in a tube, we have a mass that's suspended by springs on either side to some fixed reference. Under no deceleration, so when the car is not moving or moving at constant speed, the mass is exactly midway between the two reference points on either of its sides, and the springs are of the same length, so neither is expanded or contracted. When you start to decelerate, due to inertia, the mass moves toward one side and away from the other. One spring expands, the other contracts. And we can use that to measure weak and stronger acceleration. One of the advantages, actually, of an accelerometer as opposed to a ball and tube sensor is that the output is not binary or digital. It's not just yes crash or no crash. We can actually measure the magnitude of the acceleration. And conveniently for us, it turns out that the acceleration is proportional to the spring displacement. So let's look at this up close. So remember some of our high school physics, and if we've got acceleration A and mass m, we know that our force is equal to m times a. And also from high school physics, we know if we have a displacement x and a spring constant k, the force is equal to about, at least first order, minus k times x. If we make those two things equal to each other, rearrange some terms, forget a minus sign, we find that the acceleration is indeed proportional to the displacement of the spring, and the proportionality constant is, constant. It doesn't change once you've produced or fabricated your accelerometer. So for us, that's a good thing. What do these things look like in real life? This structure is what a single-axis accelerometer looks like. This is a pretty old part, as you see, but it's a very good way to illustrate what an accelerometer looks like on the inside. So in yellow, the proof mass, in blue, the springs, and in red, the back and forth motion or acceleration. Here's another view. Springs in blue, proof mass in yellow, and acceleration or movement shown by the red arrows. Now, looking up close, you can see that this structure is actually suspended and free to move, and so that's what allows the structure to move in response to acceleration or inertia. So that's actually the special feature of an accelerometer. Now, the way we measure the displacement is using sets of what's called fingers. So these are interdigitated fingers. The proof mass has fingers that come out of it, and each proof mass finger is straddled by two fingers that are connected to the fixed reference or the substrate. And the proof mass finger, along with the two fingers that straddle it, form a pair of differential capacitors. So here's a diagram of what that looks like up close. You see a proof mass with fingers connected to it, and two fingers straddling each proof mass finger, and the fingers that are straddling are connected to the fixed substrate. C1 and C2, shown here in red, represent the capacitors or the capacitance between the proof mass finger and the fixed fingers. And we monitor the differential capacitor pair to determine whether the mass has moved. So if the mass moves, the pair will become unbalanced, and the imbalance can tell us the amount of displacement, which in turn corresponds to acceleration. So that's scratching the surface of how accelerometers work, and these are, again, a reminder of the types of motion that we can measure with accelerometers. So we've got linear motion, we've got tilt, and we've got vibration and shock. Tilt measurement is actually one of the more common uses of accelerometers, so it's worth spending a little extra time talking about how tilt is measured using an accelerometer. So it turns out that accelerometers inherently just measure tilt. In fact, they can't tell the difference between acceleration due to motion and acceleration due to tilt. And the reason that they can measure tilt is because of a force we know as gravity. What happens is if you have an accelerometer that's not tilted, and of course not accelerating, its mass, as before, when in a balanced state, will be suspended exactly midway between the two springs. So the two springs will be of the same length and will measure no displacement. As you tilt the accelerometer, you can kind of intuitively see that gravity will pull on the mass, pull it closer to one side and farther from the other. One string will contract or compress, the other will expand, and we'll be able to measure some amount of displacement. That displacement could either be acceleration or it could be tilt. We don't know unless we know the application, but if we know that that is due to tilt, we can convert the acceleration to an angle just using this, the sine function, or a trigonometric function. And it turns out if you calculate that, this is just a handy rule of thumb, it turns out that 1 degree of tilt corresponds to about 17 millig of acceleration. So if you read 17 millig out of an accelerometer, that corresponds to 1 degree of tilt. Analog Devices has a very complete portfolio of high-performance accelerometers, some function specific, some more general purpose for high G and low G spaces. One product we wanted to highlight is a product called the ADXL362. This is a product that was released around September of 2012, and its claim to fame, or its outstanding feature, is that it is by far the lowest power consuming MEMS accelerometer that we know of on the market today. It consumes just under 2 microamps when measuring data at 100 Hertz data rate, and it can consume as low as 270 nanoamps in a wake-up mode in which it wakes up periodically to sample acceleration. In addition to consuming very little power itself, this accelerometer is also designed with system-level power savings in mind. So it's got features that enable it to act as an autonomous motion-activated switch. So it'll turn a system's power on when it's moving and turn it back off when it's not moving. And it's got some enhanced activity and inactivity detection capabilities, as well as a deep FIFO that allows you to unburden a microprocessor or allow it to sleep for longer periods of time. Now, in addition to accelerometers, Analog Devices also makes, as we mentioned, gyroscopes. Gyroscopes measure rate of rotation, and measuring rate of rotation turns out to be slightly more complicated than measuring acceleration. So how do we make a gyro? So if we have a good accelerometer, which we already have, we talked about that, to make a gyroscope, we can add to the accelerometer some gizmo, something that converts any rotation to a force, and then some coupling mechanism that can transfers that force that's generated to the accelerometer, displaces the accelerometer, and the accelerometer can then measure the amount of force, and we can back calculate the rate of rotation. The force that we use, or that we rely on for making gyroscopes, is what's known as the Coriolis Effect. In plain English, what a Coriolis effect is, when you've got a mass that's moving in some periodic fashion in one direction or along one axis, and you rotate it around a second axis, that will create a force and a motion in the third axis as well. So what we need to do is we need to somehow oscillate this mass, and then when a user in an application rotates it, we can measure that effect by measuring the Coriolis force that's exerted. So there's our gizmo that converts rotation to a force. Now we need a coupling mechanism to transfer that force into the accelerometer. Well, how do we do that? Basically, in the most simple terms, we cut a hole in the accelerometer and stick the oscillating mass in there. And that's, to a very first order, a very superficial description of how we make our gyroscopes. This is a slightly more detailed diagram of what the mechanical sensor of a gyroscope actually looks like. So you can see in the middle the resonator, the thing that moves back and forth, and around it the accelerometer frame. And you can also see the fingers, so moving fingers and fixed fingers, just like in the accelerometer, that measure the up and down displacement that is a result of the Coriolis force. So with no rotation, the mass just sits there and moves back and forth all the time. As soon as you apply rotation, in addition to moving back and forth, the mass also moves up and down. And that up and down motion is what we can measure using the fingers. One potential disadvantage of this gyro structure is that it can't easily differentiate between displacement that's caused by rotation and the Coriolis effect and displacement that's caused by acceleration or vibration. So if we accelerate or vibrate this gyroscope, the displacement experienced by the fingers is exactly the same displacement that would be experienced if the gyroscope were rotating. And this produces a measurement error in my system, which is undesirable. So what we do about this, one of the things we do about this is that we use essentially two gyroscopes back to back. So two gyroscope masses coupled differentially and resonating therefore in antiphase or 180 degrees out of phase. What happens then is that the displacement or the signal resulting from rotation is a differential signal, so we measure it. And the displacement or signal resulting from acceleration or vibration is a common mode signal, so we cancel it out. This is what a gyroscope actually looks like. So this is a picture of the mechanical sensor of a two-mass differential gyroscope. And two-mass gyroscopes are a lot better than single-mass gyroscopes at rejecting the effects of acceleration or vibration, but they still have these problems, just to a lesser extent. So if we'd like to improve upon this even further, which we did want to do, the next logical step was, yes, you guessed it, put four masses together and cross-quad couple them so that they can only move in response to differential signals like rotation, and they cannot move due to common mode signals. So this design has actually allowed us to achieve excellent vibration and acceleration rejection in our latest line of gyroscopes. We have, just like our portfolio of accelerometers, we also have a complete portfolio of gyroscopes and IMUs, and it's shown here for your reference. The gyroscope product we'd like to highlight is the ADXRS64X gyroscope series. This is a family of high-performance gyroscopes made using the quad-mass sensor structure shown in the previous slide. The structure makes these gyroscopes very good at rejecting vibration. So the response to both linear acceleration and vibration rectification are excellent compared to other gyroscopes on the market. This family of gyros is pin and package compatible to the previous generation, the ADXRS62X family. And there are a couple of different flavors of this gyroscope to hopefully suit all of your needs. So far we've talked only about MEMS motion sensors, but Analog Devices also makes MEMS microphones, so basically MEMS sound sensors. These obviously don't measure motion, but they operate in much the same way that the accelerometers do, and I'll tell you why in a minute. The technology for microphones in today's world is moving away from the standard electric condenser microphone in a lot of cases and toward MEMS microphones for a lot of the reasons listed here. The MEMS microphones are more resistant to mechanical shock, to temperature, to solder reflow. They're a lot better matched part to part, and this helps when doing things like noise cancellation, beamforming. And they have higher SNR and they consume less current. So a lot of these advantages are causing or convincing the industry to switch from electric condenser microphones and move toward MEMS microphones. The way that MEMS microphones work is they're made up of a diaphragm which is suspended on springs above a backplate. When the microphone is subjected to sound, the air pressure from that sound causes the diaphragm to move up and down, and we can measure that motion based on the change in capacitance between the diaphragm and the backplate. This might sound familiar from accelerometers, so we're using capacitance again to measure displacement and using that measurement to back calculate the measurand that we're interested in. In analog devices microphones, the backplate is actually perforated, as shown here, to both allow air pressure in and also keep dust particles out. Just to get a sense of how much the microphone diaphragm moves in response to different sound levels. In response to normal conversation, the microphone diaphragm would move about 5.5 angstroms. And in response to a crying baby, so something that would probably hurt the human ear, the diaphragm moves about 1700 angstroms. So both of these are not huge amounts of motion, not huge differences in capacitance, but we at Analog Devices have been making accelerometers for years. We know how to measure very small differences in capacitance. So we make what we like to think are pretty good MEMS microphones. So some of the advantages of MEMS microphones over the electret microphones. One of them is that electret-based microphones can deliver very high SNR and they can be very small size, but they can't be those two things at the same time. The MEMS microphones both shift the SNR curve up and shift the size down, so you get a much better SNR per physical volume. Another advantage of MEMS microphones is their stability over temperature. So shown here in this graph is the sensitivity of 5 different microphones as their ambient temperature is swept from -40 to 85 degrees Celsius. And you can see that the sensitivity of the Analog Devices MEMS microphone, which is the black line in the middle, stays pretty steady over the entire temperature range, whereas the electric condenser microphone sensitivities change widely and somewhat unpredictably over the temperature range. One thing to note is that all of Analog Devices microphones, MEMS microphones to date, have a bottom port configuration, which means that the hole that lets sound into the microphone is on the bottom of the microphone and needs to be mated with a hole in the PCB when the microphone is soldered into a system. There are MEMS microphones out there that have a top port configuration, and we often get asked the question, well, why don't you also make a top port microphone? Well, in our microphones, we're striving for high performance, and the bottom port configuration enables us to achieve a superior SNR, but more significantly, a superior frequency response as compared to the top port microphone. If we look at the frequency responses of these two microphones and compare them to each other, you can see that the bottom port microphone has a pretty flat frequency response, which is what you might expect or might want. But the top port MEMS microphone has a sharp peak in its frequency response right around 10 kilohertz, which is well within the audio band. The reason for this peak is what's called a Helmholtz resonator between the port and the diaphragm of the microphone, which in the top port microphone, the resonator cavity is fairly large. It's the entire cavity of the microphone. In the bottom port microphone, the resonator cavity is small. It's just the portion that sits right underneath that diaphragm. So a large cavity results in a lower resonant frequency and pushes that resonant peaking into the audio band, whereas the small cavity results in a much higher resonant frequency, and the peaking does occur, but it's somewhere at much higher frequencies where it doesn't matter to us. So all top port microphones on the market currently have these sharp peaks in their high frequency response, and this makes them unusable for wideband voice applications. Top port microphones also have lower SNRs, or signal to noise ratios, than what we achieve with our bottom port microphones, and to date there are no top port microphones with high performance that are currently on the market. Analog Devices makes a range of microphones, ranging all the way from the simplest analog output microphone and up to the ADMP441, which is the world's most integrated digital output microphone to date. The ADMP441 uses the I2S digital interface, which is a very common interface for digital audio, and it's built natively into a lot of digital signal processors and some microcontrollers, allowing for simple connection. And I show here the portfolio of Analog Devices MEMS microphones that is available on the market today. And with that, I thank you for your time and for your attention, and I'll turn it back over to Dave Kress.
Well, thanks, Nitzan, for your excellent coverage of our MEMS sensors for motion and sound pickup. What we covered today, again, is that sensors are the source of information from our physical world. And we looked into some of the aspects of how they're difficult to use, but how signal conditioning can extract that signal and make it useful for our systems. We also learned that silicon sensors are able to give us much better performance because they are integrated directly with the signal conditioning, especially important because there is higher and higher demands for accuracy from all sensor types. We also looked at a few types of motion sensors and the great degree of sensitivity that they can provide for many different applications. Also, silicon microphone sensors are improving performance in sound capture. We covered several products today that we'd like for you to look at in many different areas as sensors as well as signal conditioning devices and motion sensors. Thanks again, and please join us for our Q&A session.